Hello, Mrs. Belo here. In this video, I'm going to be going over limiting reactants in the notes, slides 19, 20, and 21. So let's get started. So a limiting reactant by definition is the reactant in a chemical reaction that will be completely used up. Its name makes sense because it limits how much product you can get out of the reaction. So again, we're talking about chemical reactions here, like either synthesis or single replacement, double replacement, something where you're going to get product, and the limiting reactant will be the reactant that pretty much controls and limits how much product can be made. Excess reactant, this is the reactant that you will have leftovers of. It's what's, you have remaining after the chemical reaction has occurred. In a perfect world, chemical reactions would be in these perfect ratios, everything would be used up, but in reality, that does not happen a lot. Usually something will be used up first and you have leftover of some, because you're not always going to have 100% of the product being made. That's just how real world works. And again, remember the reactants, that's on the left-hand side of the reaction, okay, to the left of the arrow. And the products are on the right-hand side of the reaction, to the right of the arrow. So let's say we have a chemical reaction here. We have a simple synthesis reaction. We're going to get methanol, which is a simple alcohol, and it's from the combination of carbon monoxide and hydrogen. Here's the balanced equation. So in order to figure out which of these two is limiting how much product can be made, so which of these two are we going to identify as the limiting reactant? Well, what we can do is just a simple picket fence, pretty much what you've already been doing. But the thing is we're actually going to take both of these values that we're given, and we're going to convert both of them into the same product, because then we can compare, again, this is all theoretical stuff we've been talking about. We can compare theoretically which one would produce more product. So we're going to convert each reactant into the same product. So you will have two picket fences, okay? And you're going to convert them into the same product. Now, in this case, we only have one product to pick from right here. If you have multiple products, for instance, here, you just have to pick one of them and you can convert both into the same. As long as you're converting them both into the same product, then you can see, which one is going to make more product, which one would make less product. And the one that produced the least amount of product, that's going to be your limiting reactant. Again, what we've been doing with stoichiometry is simply all theoretical. If I have this much reactant, how much product will I make? If I have this much product, how much reactant would I need? That's all we're doing with the moles and the grams when we're converting them. Okay, so here is our balanced equation, and then we have our two reactants. So I'm going to do a separate picket fence for each one. So we have 500 moles of carbon monoxide, CO. And then our other picket fence, we have 750 moles of H2, or hydrogen gas. So this is a pretty easy picket fence just because we're starting with moles to begin with. If you were starting with grams, you would have to convert grams into moles first by finding the molar mass. But we're starting with moles, so we can actually go right into using the mole-to-mole ratio from the balanced equation. So I'm going to do this picket fence first. So I'm going to figure out if I have this many moles of CO, which is carbon monoxide, how much product would that produce, theoretically speaking? So again, this is a picket fence. If I have moles of CO here, I know I have to put moles of CO here. how many moles? Well, I'm going to get that number from the balanced chemical equation. Again, there's a 1 as a placeholder there. So in the bottom, I have 1 mole of CO, which is carbon monoxide. And again, since I got that number from the balanced equation, the number that goes above it should also come from the balanced chemical equation. And what I want to convert it into is this product right here, which I also have 1 mole of. CH3OH. So luckily for us, there's not a lot of math to do here because it would be 500 moles times 1 divided by 1. And I don't want to forget to do this. Moles of CO cancel on top and bottom. I'm only left with moles of CH3OH. So if I had 500 moles of CO, which is carbon monoxide, that would produce 500 moles of CH3OH. Now, this is not my final answer. My final answer should be which of these two reactants is the limiting reactant. And it's whichever one we're going to have less of. So now we have to do this one right here, this reactant, which is the H2. So pretty much the same thing I just did in the previous picket fence. So I'm going to convert moles of H2 into moles of CH3OH. So if I have moles of H2 here, I know I have to put moles of H2 here. Well, how many moles? It's going to be 2. And again, I'm getting that from the balanced chemical equation. And again, I want to convert this into the same product, which is this guy right here. So I'm actually going to write 1 mole of CH3OH in the top here. Again, we're getting that from the balanced chemical equation. So for this math, we're going to have, before that, I'm going to cross off moles of H2. So I'm only left with moles of CH3OH. So this time we have to do 750 times 1, which is 750, and then divided by 2, which is 375 moles of CH3OH. So we're seeing if you had that much of each reactant and you converted it into product, how much product would it make? Again, this is not my final answer, actually. So since this one made less product, 375 moles is less than 500 moles, that means that H2, because I'm talking about the reactant, H2 is I'm just going to write LR. That would be acceptable for limiting reactant. And that would actually be my final answer. Okay, so you have to show both picket fences and convert both reactants into the same product. And whichever one makes less product, that is your limiting reactant. So for your final answer, you should have circled or indicated that, in this case, H2 is the LR, which is the limiting reactant.